Yeah, sorry, I'll just start presenting from here. Yeah, I hope you can hear me now. Huh. So we were looking at this question. Yeah, sonication of cells suspended in liquid medium should be done in ice to prevent dash. And four different options were given here. We'll start with the wrong options. Anyone who knows can unmute yourself and start justifying why an option is incorrect. Yeah, you can unmute.
Osmotic shock.
Hmm,
Osmotic shock, as said before, it refers to the rupture of cells due to sudden change in osmotic pressure.
right.
So
Huh,
it does not need any medium to uh, make it cool for the ice to be present. So there is no need of ice for that.
right. Makes sense. And but would temperature affect the osmotic pressure?
So I didn't get you.
No, but okay. Would temperature affect the osmotic pressure? There is because you were talking about movement, right? Movement of water, which is diffusion, which is a temperature dependent phenomenon. So, would temperature affect osmosis?
Um, Temperature does affect osmotic pressure,
Hmm.
but I don't think ice is needed for that.
Okay, you can answer this question in a different way. Like, okay, when does osmosis happen, or when does any process happen at a higher rate, at a lower temperature, or at a higher temperature?
I didn't get you, sir.
No, no. What I was asking is, all these processes where transport is occurring now, these are temperature dependent. The rate at which these processes happen, is it higher at higher temperatures or at lower temperatures? Collision of these
Osmosis.
molecules and all of these. Any transport related phenomenon, these are temperature dependent, right? Now, these temperature dependent phenomena, do they happen at a higher rate, at higher temperatures, or at lower temperatures? Okay, I was just trying to relate how ice will might make a difference. So, ice will ensure the temperature of your solution is low. Do you agree? Can you hear me?
Yes, sir.
Yeah. So, yeah, you can hear me, right? I was just asking if at higher temperature, osmosis will be higher, or at lower temperature, osmosis will be higher.
So higher temperature osmosis will be.
Higher.
higher.
Okay, fine. Just wanted to confirm if you were, if we were on the same page on that part. Right. Right. For osmotic shock, the at least here, sonication isn't relevant to osmotic shock. What other options? Chandraman Vishwajit?
So right option or wrong option?
Wrong option.
It is not fully related with that sonication, because an inclusion body is formed when any protein is sort of degraded, or uh, it is misfolded, or it is not soluble. Actually, that is not what it's not a very complete protein in that case.
So, if a protein is not soluble, it will not be present in cytosol. Rather, it will go into a specific thing called inclusion body. Is that what you were saying?
Yes, sir.
Okay. But can ice prevent that?
Yes, sir.
You no. Do you mean to say ice will prevent inclusion body formation?
No.
Right. The thing is, these inclusion bodies are formed when the cells are growing. So, independent of us changing the temperature, it would not break open. So whatever protein that
It
goes
will
to the
not take
inclusion
place.
body, whatever protein that goes into the inclusion body will stay in the inclusion body. They will not come back to cytosol. They will not become soluble
Yes,
through
sir.
sonication. Right. Okay. Yeah. And Vishwajit?
Sir, your screen is not visible.
Oh, is it? What about others?
Sir, it's
Yes, sir.
visible.
It is
It's
visible.
visible, right? Okay.
Sir, I think I have some internet issue.
Okay.
Maybe due to that.
Okay. I'll just read it out. Once we finish this question, you can just rejoin. Is that okay?
Okay, sir.
Okay. So we were discussing this question. Sonication of cells suspended in liquid medium should be done in ice. And different options were given. We eliminated the option osmotic shock and inclusion body formation. There are two more options. One is thermal denaturation, and the other is prevent formation of cavitation bubbles.
Uh, Option C, formation
Formation
of
of cavitation bubbles.
bubbles.
Okay. Do you know what these are? Like cavitation bubbles?
Okay, so to form a like bubble which has a cavity, I mean space in it.
Huh. And how? Where is it relevant to what we are studying?
uh, in the cells, like um, I'm not sure, sir.
You can try thinking about it. And Chandrima and Rajata, even you can attempt answering these questions, like where cavitation bubbles are relevant with respect to what we are studying.
Sir, actually, don't know about that cavitation uh, bubbles, but yes, during that sonication, actually, what is creating in that cell membrane is a pressure of high pressure area and a low pressure area, due to which some bubbles get formed.
Bubbles
But
were
it is not
formed.
related with.
Hmm.
Yes, sir.
Sorry. You continue. I'll ask my question next. Yeah, continue.
So means as it forms many a times, it's not fully that pressure is not equalized, so it is getting formation of the bubbles that are called the cavitation bubbles. But in the question given that it is not linked with the ice. The ice is here to cool down the temperature, but it will not help to prevent that formation of cavitation bubbles. Cavitation bubbles will be forming that
Hmm.
case.
Okay. So to rephrase what you said, cavitation bubbles are formed when these ultrasonic waves hit a liquid media. And what we mean by cavitation bubbles is they are not like the normal bubbles that we see as perfect spheres. Rather, they have some cavity because of a difference in the pressures. And it is the breaking of these bubbles that gives this implosion energy to break open the cells. But in no way ice will prevent the rate at which this cavitation bubbles is formed because this is a physical phenomenon. Rather, this ice is needed because we want to maintain the temperature. That's what you told, no, Chandrima?
Yes, sir.
Okay, but why do you want to maintain the temperature? What is there that you that makes it essential for you to maintain the temperature? Uh,
Actually, the in that cell we are having proteins.
right.
So at that temp, if we are agitating the cells with that sound waves, it will also increase the temperature. So which could cause the degradation of the protein. Hence, we are requiring that ice so that it can cool down or maintain the temperature.
Okay. So at higher temperatures, what are the possibility that the protein would degrade? Is it high or low?
So it getting denatured.
Proteins get denatured at higher temperature. The possibility that it would get denatured is higher, right?
Yes, sir.
Okay, right. So, like we discussed, the reason why sonication is done on ice is because once you sonicate, the cells would start to break open. As they break open, whatever is present on the cytosol, majorly the overexpressed protein, will get released. Now, once these overexpressed proteins are released, it is always essential to keep them at a lower temperature so that they don't undergo thermal denaturation. So, our interest is to protect these proteins from thermal denaturation, which is why we do the sonication on ice. So, yeah, we'll go to the next question. Huh. Now we go to a question that previously we had a brief discussion about. This is about lipid saponification. So the question is, lipid saponification is the result of treatment with option A Triton X100, option B alkali, option C STS, and option D toluene. Right, because we had discussed this question in the first question itself, I'll directly go to the chemical reaction so that we save some time on this question.
Sir, the
Yeah,
question is not visible.
are you able
Question.
to see my slide?
Yes, but the question number four, that sonication question, I am able to see, but
Oh,
not question number five.
what about others? Vishwadhi, Rajata, and Yogita? I moved on to the next
See, sir.
slide. You're able to see?
I'm seeing the fourth question.
You're able to see the fourth question. Let me stop sharing and share this again. Right. Are you able to now see my slides?
Yes, sir.
Okay. So the question is lipid saponification is a result of treatment with four different options are given here. Triton X100, alkali, STS, and toluene. Because we were discussing earlier about what lipid saponification is, where we have a triglyceride and an alkali. So now what would happen is all these carboxyl groups will be removed, and instead you will have hydroxyl groups here, and these carboxyl groups would form soap. Here the alkali is NaOH, because of which we have a sodium salt. Whereas in the other cases, if we use KOH, we'll have potassium salt. So this is the chemistry behind saponification. The next question, the enzymatic digestion of yeast cells would result in the formation of four different options are given here: micelles, spheroplast, cytoplast, and nucleoplast. Earlier, 2 weeks back, we discussed about the specific treatment of yeast cells with specific enzyme. So we had also looked at how the periphery of a cell would be dissolved. Now the question is, what is this new thing called after dissolution of the periphery? There is not much to think about this question. If anyone knows, you can unmute your mic and try to answer this.
Option B.
Spheroplast. Okay, right. Like we showed in the last time, upon treatment with this zymolase, you see that it is completely empty and it forms something called as a spheroplast. Huh. The next question is about cell disruption. So cell disruption in a bead mill and release of product follows dash order kinetics. Then four different options are given here. Uh, so, before we go on to the right answer, the anyone who would like to answer can first discuss about what this bead mill is, and then we would go on to the kinetics. We can take a couple of minutes and then start to answer. Yeah, Chandrima, we'll start with what a bead mill is. Yeah, Chandrima, we'll start with what a bead mill is.
Actually, bead mill is like a term where you are having a grinder like impeller which will be rotating in a clockwise or anti-clockwise fashion, and it will become, and inside that system we are having a beads made of alumina or zirconium oxide, and also having an inlet from which the cell suspension we can give.
Hmm.
And after churning those, or after running that bead mill, like it's a just like a churning process,
Hmm.
then we get the result, we the resultant solution out from an outlet. It's like it is that bead mill
So
what
it's for
happens.
a it is a physical method,
It's a mechanical method.
mechanical method, right? Hmm. So If that's the case, now the release of products follows dash order kinetics. Is it easy to estimate the kinetics?
Actually, we can see by the concentration of it.
So you put a particular amount of cells, and upon lysis, you see a particular amount of product. The product could be your desired product. Based on which, can you formulate an equation, and is that how you can do this?
Yes, we can.
Right. Yeah, that's the way to do this. And one more question about this method because we haven't discussed about this method. So you're saying this Beadman is a mechanical method. Now, cells are of different sizes. A bacterial cell is literally very small compared to a mammalian cell. So, in a bead mill, would something change because we are using a different cell type? Should something change?
We can change that bead size.
Hmm, right. So, according to the type of cell that we are taking, we need to change the size of the beads. Only then, upon agitation, this beads can lyse the cells. Right. Good. Yeah. So, like we had discussed, you know the amount of cells that you are allowing to enter into the bead mill, and depending on the concentration of the product that is released at a given time, the reaction rate constant can be calculated. And for the batch mode operation, it is estimated that this is of first order kinetics. Although they say that this value of this rate constant depends on other uh, variables like the bead size and the type of impeller and the speed. The next question is, which of the following equation describes the dynamic pressure experienced by cells in a high pressure homogenizer? The four different options are given here. So, before we go on to this question, anyone who would like to answer can describe how this homogenizer works. We'll take it from there. Yeah, anyone can unmute and describe how this homogenizer works. High pressure homogenizer.
Sir, in a homogenizer, what is happening? the cells or the cell suspension, it is undergoes in a very high pressure
Hmm.
to a pump,
Hmm.
and due actually as it is having that high pressure, it will experience a shear stress within. Actually it is also having a fluid, so which is causing that shear stress, due to which that cell membrane gets disrupted.
Right. So how do we achieve this high pressure?
So the high pressure, it is actually it is having a pump, high pressure displacement pump, which is actually giving that pressure.
Huh. So, okay. You are saying that there's a pump. Can you correlate pressure to area through which the fluid flows? Let's say there are two surfaces, one that is narrow, the other that is wide. Now, if a fluid is flowing through the narrow surface, whereas the fluid is flowing in a wide surface, which of these would undergo high pressure? Given a particular velocity, which of these would undergo higher pressure?
Which is having an higher area,
Huh?
which it will go comparatively less, but which is having a very narrower area, it
Huh?
will experience high.
Right. Yeah, that is the principle that we wanted to discuss specifically with respect to this question. So, in these homogenizers, you have a uh, narrow uh, gap through which the fluid flows, and this, owing to its narrow volume or area, a higher pressure is generated. That is what helps in generating the shear force and then helping in breaking opening the cells using this mechanical method. Was that clear?
Yes, sir.
Right. So now we have to correlate that using an equation. So that is given by Ps is equal to half into PV square or rho V square, where Ps is the dynamic pressure, V is the velocity, and rho is the density. This is a general mathematical equation. The reason I was asking about this, uh, the correlation between the area and the pressure, is to describe about how this pressure is generated. Only when a narrow tubing is used, you can generate such a high pressure. And that's how we will be able to correlate this inverse relationship as well. The next question is the distribution coefficient Kd value of x, y, z are 1, 5 and 10. A mixture of an equal amount of x, y and z are injected into a column. The order of their elution is, and four different options are given here. So before we go discuss the options, uh, one can start with discussing what the distribution coefficient means. We can start there and then describe how distribution coefficient can decide the order of elution. Okay, we can take a couple of minutes, and whoever knows about the distribution coefficient can unmute and start to uh, explain what it would mean with respect to order of evolution. Yeah. Does anyone want to try answering what a distribution coefficient is?
Sir, the distribution coefficient is what we determines how an analyte is distributed in two phases, that is stationary and the stationary phase and the mobile phase. How it is distributed?
Okay, so does that mean it's a ratio?
Yes, it's a ratio.
Okay, okay, so it's a ratio that would tell you how a particular analyte gets distributed when there are two different phases. Okay, so if that's the case, a distribution coefficient value that is lesser for a particular analyte, would that mean it distributes well or if it doesn't distribute well? For example, the value of 1 here for x, does it mean it is getting distributed well or not with respect to the value of 5?
Lesser value
Hmm.
determines that it's not distributed well. Not clearly it is distributed, well distributed in that column. It is less distributed.
Okay, lesser value means it's less distributed.
Yes,
And 10 here means it's more distributed.
yes.
Okay. What about others? Yogita, Rajata, and Vishwajit. Do you agree? Can you hear me? Rajata, Yogita, and Vishwajit?
Yes, sir.
Yeah, so do you agree that lower the values of distribution coefficient, the lesser that they get distributed into a column or into another uh, liquid medium?
I'm not sure, sir.
Okay, do you know about the distribution coefficient?
Yes, sir.
Okay, you can tell us what you know. We'll take it from there, Vishwajit.
Sir, is it on uh, uh, based on size and charge?
It would be dependent on the properties. That is true. But what exactly does this term distribution coefficient means? Do you know that?
No, sir.
Okay. So briefly, you can understand that the distribution coefficient. So you have a particular molecule, and you have the molecule can interact with two different substances. For example, the beads in a column and the solution in which the molecule is present. Now, this distribution coefficient will help you tell whether it is more likely to stick to the beads or more likely to stay in the solution. So there is a ratio that determines this. If you have 100 molecules, 10 will stick to the beads and 90 will fall down, as in they go with the liquid. This can be a brief definition for how distribution coefficient works. Now, depending on
So,
this, if you inject something into a
yeah,
column, if the distribution coefficient is good enough, like for example 10, that means it would stick onto the column. Do you agree with that?
yes, sir.
Okay. So that is why we have the order here as okay. X, Y, and Z have 1, 5, and 10 as distribution coefficients, meaning Z will stick onto the column for a maximal amount of time, followed by Y, followed by X. Now, because X is sticking for very few relatively lower time, X will be eluted first, followed by Y and followed by Z. Do you agree with
Yes,
this, Chandrima and
yes,
Vishwajit, based on the definition of distribution coefficient that we have discussed?
yes, sir.
Okay, yeah. So this is a slide from the course. Here also we see as to how particular values of KD would allow it to partition between the two phases. And the one with the lower distribution coefficient will be associated with just the liquid in which it is dissolved. So it will elute first rather than going to the beads. The next question is a chromatography column has a length of 100 centimeter with 1 centimeter height of distribution plane. The number of distribution planes of the column is, and four different options are given here: 1, 10, 100, and 1000. So we can take a couple of minutes and then uh, discuss on what is the relation between the height of the distribution plane and the length of the column. Anyone who knows can raise your hand. Understood. Understood. Yeah, Chandrima. What is the relationship between this distribution plane and the column?
Distribution is it's a formula exactly. N equal to L by H, where it
Huh.
is the N is the length and the H is the height.
Hmm.
So by calculating, we can get the number of distribution plane in the column.
Okay. Now, going on to what distribution plane is, does the distribution plane actually exist, or is it a theoretical concept? Yeah, Chandrima. Does the concept of distribution plane exist, or
So it's actually a theoretical aspect, we can say.
okay? So, can we say that based on how the beats are arranged, theoretically we can divide each, okay, the beads ideally should be dispersed uniformly, but need not be the case because they are very tiny of micron size. Because of which we assume that if the beads are all perfectly formed as a single layer, it can be called as a distribution plane. Uh, do you agree with how we define this distribution plane?
Yes, sir.
Right. So, if that's the case, what would be the answer here for a length of 100 centimeter, 1 centimeter height distribution plane? What is the number of distribution planes?
100.
100. Right. Right. The definition, the relationship that you told is mentioned here. N is equal to L by H. And the length is 100 and the height is 1. So the number of distribution planes are 100 here. Okay. Okay. The next question is, which of the following property of a protein is exploited in gel filtration chromatography? Charge, affinity, surface area, and hydrophobicity. So we'll take a couple of minutes, and if anyone would like to answer, you can start with explaining what gel filtration chromatography is. We'll take it from there. Yeah, so does anyone want to unmute and explain what gel filtration chromatography is? Okay, if that's not the case, we'll start with the different options given here. Okay, yeah, Chandrama. Before we go to what gel filtration exactly is, do you want to eliminate different options here? Like, for example, charge is given. What is the kind of chromatography that makes use of the property of charge?
Ion exchange chromatography.
Right. And what are the kinds of ion exchange chromatography that we have?
One is cation ion exchange chromatography and another is anion.
Right. So that is not gel filtration. Okay. And what is affinity based chromatography?
Sir, in affinity, it is having like the molecule is joined with a particular affinity tag. It is tagged with a particular molecule,
Okay.
so that when it molecule comes, it could separate those, and we can extract that protein.
Okay. Did we discuss of any affinity related chromatography previously in the last class?
Yes, we are talking about the GST,
GST and
glutathione,
that is
I think.
GST is glutathione S transferase. And did we discuss something else as well?
His tag.
Yeah, his tab. So nickel and TA. Yeah. So these two are affinity. Okay. Now we'll come to gel filtration. Yeah, Chandrima.
Sir, in the gel filtration is having like we are separating the proteins. It is having a pores,
Hmm.
and it that the particles which is getting separated, it is in the basis of the sizes of
Right.
that protein. Based on
Right.
the sizes, it is getting uh, placed exactly.
Okay. So let's say there are two protein molecules. One is of larger size, one is of smaller size. Now, what exactly is expected when these both these proteins are traveling through a gel filtration column?
If it is in a gel filtration column, it is having a pores.
Hmm.
And into that pore, that smaller one will be getting inside, more inside into that pore, and that the larger one is comparatively outside. Actually, in these pores is having a certain amount of sizes determined. If it is exceeding, then it will be remain out of that pore.
So the way to think about this is proteins that are smaller in size have to go through the pores of the beads, meaning the path that these smaller proteins would take is longer. The time it would take to reach is longer. Whereas the large proteins will not enter these pores and they would go between the gaps between these beads. So that means larger proteins will get eluted first and smaller proteins will get eluted later on. Do we agree on this?
Sir, can you repeat it?
Yeah, yeah. So what I was telling is in size exclusion chromatography, you have beads. And within the beads itself, you have some pores. Now, proteins of different sizes. Smaller proteins that can go into the pores will enter the pores. So that means the time it would take to reach the end of the column is longer because the path that these smaller proteins would take is longer. Whereas the larger proteins will not enter the pores but will rather go away from it because of its size, also the surface area. That means the time it would take is lower. So it will elute first and the smaller protein will elute later. Was that clear, Vishwajit?
Yes, sir.
Okay. So we exploit this property to separate proteins in gel filtration. So it is basically the surface area and not hydrophobicity. So whatever I was mentioning is given here as a text. So here it says that bead size can affect the width of the eluting peak, therefore resolution. Beads that are smaller have larger surface area to volume ratios, which increases the contact area between the beads and it would improve the resolution. Although this is not exactly how we discussed about size explosion chromatography, some aspect about the surface area is also mentioned here. The next question is a mixture of four proteins with their charges in phosphate buffer of pH 7.4 are as follows: A, B plus 1, C plus 2, D minus 1. The protein dash will bind strongly to the matrix of an anion exchange column. So, to answer this question, we need to know that what anion exchange is. So, we'll start with defining what gets exchanged in the anion exchange column, and then we'll take it further. Yeah, so we'll discuss with what anion exchange column is or what anion exchange chromatography is. In anion exchange chromatography, what gets exchanged? Does anyone want to answer? Rajata, Vishwadit, and Yogita?
Sir,
Yeah.
sir, in anion exchange column,
Hmm.
it has a positive charge on it, so
Okay.
it attracts negative charge protein.
Huh.
So option D will be the answer.
Right. Yeah, that is pretty straightforward. So in anion exchange, you have a positively charged particle, like you mentioned, and negatively charged proteins will bind. Now, Vishwajit, what do you think will make a protein positively charged or negatively charged?
Sir, pH.
Is it only the pH or is there something inherent to the protein?
It's um, CH COOH or uh, NH3 this thing.
The amino group.
Um,
It's either the
yeah,
carboxyl group or the amino group. But what about the side
yes,
chains? They also contribute to the charges, right?
yes,
So each amino acid has a particular pi, right?
yes, sir.
Pi is the isoelectric point, the the pH at which there is no charge for the amino acid. And because proteins are made up of amino acids, the protein itself can have a particular pi. Do you agree?
Yes, sir.
Yeah. So now, depending on whether the pH is greater than the pi or the pH is lesser than the pi, we will decide whether the protein will be positively charged or negatively charged. Now, suppose the pI of the protein is 5.6. Now, the pH of the solution is greater than 5.6. Let's say 7.4, like in this case. So, what do you think will happen there?
Sir, it would not bind to the column.
No, no. What I was asking is, your the pH of your protein is 5.5, pH of your solution is 7.4. Your pi is lesser than pH. Okay, now you can understand it this way. At pH 5.5, your protein has zero charge. Now you are increasing the pH. So will it gain a positive charge or will it gain a negative charge?
Sir, negative charge.
Your protein will gain a negative charge.
Yes, sir.
What about others? Do you agree? Your pH is greater than pi. Others? Rajata, Chandrima, and Yogita. What do you think will happen if pH is greater than the pi?
Sorry, sir, I'm not able to hear.
Okay, so we were discussing about this anion exchange chromatography. Then we moved on to the concept of pi, which will decide whether you need to use a cation exchange or anion exchange. Theoretically, let's say a protein has a pi of 5.6 and the solution pH is 7.4. Now, at this pH, what will be the predominant charge of your protein? Will it be positive or negative?
It will be negative.
It will be negative.
No, no, it should be actually positive because it is having H plus ions more, so it should be positive.
Uh, Vishwajit,
No,
you
sir,
were
it should be negative.
okay. We'll have to come to a conclusion. So you will have to justify why it will be positive or negative. That will help you understand better and decide whether you have to use anion exchange or cation exchange. Take a couple of minutes and then we will listen to each justification. Okay. Yeah, we'll start with Rajata. What do you think will happen when the Pi is lesser than the pH?
So there will be deprotonation.
Okay.
So acidic say, side chains like acidic residues are
Hmm.
deprotonated and lose a proton, and they
Huh.
become negatively charged.
Okay.
While basic side chains, basic residues like lysine, arginine remain protonated and positively charged until the pH rises further.
No, no. Are they protonated or are they unprotonated? Like you have NH2 which can go to NH3 plus or remain as NH2. Is it like do they remain NH2 or do they go to NH3 plus?
I didn't get you, sir.
No, you said the what you said for the acidic side chains are right. The COOH groups would turn negative to give COO minus. Agreed with that. What about the NH2 groups? Do they get converted to NH3 plus or do they remain as NH2 when the pH is greater than the Pi?
So they remain same.
Huh,
They
they
do not
remain
lose their
same.
protons. They remain the same. But
Right,
since the acidic group it's getting deprotonated, the overall charge will be negative.
right. Okay, I agree with this. Chandrima?
Yes, sir.
Yeah, so we were discussing about this, and you said the protein would have a positive charge.
Yes,
How?
sir.
But why do you think it will have a positive charge?
In case of pH greater than isoelectric point,
Huh,
but sir, when I have realized that when we are having greater in the that the pH greater than that isoelectric point,
huh,
that the solution is having more OH minus,
right.
and it will be negatively charged.
Huh. So the protein will be negatively charged or positively charged in that case.
It will be negatively charged.
Okay, so you also agree on that. And Vishwajit?
Yes, sir. It will
They will.
negatively charged.
Okay, great. Okay, that was just for clarity. No issues. Okay. Uh, yeah. The next question is, which of the following is an ion exchange matrix? Is an example of anion exchanger. So, how do you decide whether it's an anion exchanger or a cation exchanger? Does anyone know based on the functional groups here? This can be in the form of discussion. You need not know, but just based on the naming. So, I can tell you how you can think about this. The methyl, propyl, and ethyl groups, these are linkers. These are alkanes. They do not have any charge. So, what you need to look at is the carboxyl or sulfo, sulfonate, and amino. Based on this, can you decide the charge?
Sir, option A, carboxyl methylene. Methyl.
Carboxyl methyl? Huh. What do you think will be the
So
charge of this?
it will be negative.
If it's negative, will it be okay? It is negative. What about others? What about amino groups?
It will be positive
Right,
charge.
right. What about sulfur or sulfonate groups?
About that, I don't have any idea.
Think about it. You were saying about carboxyl because it's an acid, it's a derivative of an acid which lacks a proton. You told it's a negative, right?
Yes, sir.
Same as the case with sulfonate, sulfuric acid's derivative. Let's consider it that way, and sulfopropyl as well. If you look at it, most of these Just based on how their names are, you will be able to guess. Like amino groups are positively charged, and if it's positively charged, it's just anion exchanger. Whereas if it's negatively charged, like carboxyl or sulfur or sulfonate, it is a cation exchanger. The structures of which are given here. Okay. Huh. So the next question is relevant to what we were discussing earlier. They say that the pI of a protein is 6.5. Which of the following buffers should be used so that the protein could bind to cation exchange column for purification? Now, think about the discussion that we had a few minutes back. Your protein is your protein's pI is 6.5 and you want to do cation exchange. That means your protein should be positively charged. When is your protein positively charged?
At lower pH.
Right. So which of these has a lower pH compared to the pI?
Option
Option
C.
C.
Option C. Right. So that's how you decide here.
Sir, is there any difference in the buffers, like carbonate buffer, phosphate buffer?
So with respect to the buffering capacity, some of these cannot buffer a higher range. So what you call as the buffering range is the pH beyond which the buffer loses its ability to maintain the solution's pH. Like for example, phosphate buffer has a capacity till around 8.5, from 6.7 to around 8.5, which means that if you add more of NaOH, make the buffer's pH beyond 9, your buffer will not be able to maintain the pH and bring it back to the original pH. So this is something that is unique to the property of the buffer. Other than this, some of the buffers also have something called as heats of dissolution, meaning when your buffer is trying to exchange protons and make sure the buffer pH is maintained, some of these buffers release heat or some of these buffers take in heat, others do not. So these are something that are specific to the properties of the buffer. Did that answer your question, Rajita?
Yes, sir.
Huh. But with respect to this ion exchange, the name of the buffer doesn't matter as long as the pH is ensured.
Okay, sir.
Right. And the last question is, addition of a low amount of salt could facilitate the solubility of the protein. This effect is known as, four different options are given here: aggregation, salting in, precipitation, and salting out. So, uh, does anyone know this concept of salting in, salting out? Okay, before we go to that, we can. Are you able to hear me? Ayo. Yeah, sorry, I lost internet connection. Can you hear me now? Okay. So the question was about addition of salt, improving the solubility of a protein. And four different options were given there. Aggregation, uh, precipitation, salting in, and salting out. When we say we improve the solubility of the protein, how is it relevant to precipitation and aggregation? Can someone correlate these terms? Improving solubility and precipitation and aggregation? Yeah, Chandrama. Yeah, Chandrama. You're on.
Was not able to hear that question.
Okay. Okay. The question was addition of a limited amount of salt improves the solubility of a protein. Now, what is this effect called? Is it called salting in, salting out, precipitation, or aggregation? But before we go on to the right answer, I just wanted to ask if you are aware of what what is the relation between improving the solubility of protein and aggregation and precipitation. You're on mute, Chandrima. Yeah, Rajita.
Sir, aggregation results in decreased solubility.
Right. So, what exactly is aggregation?
So, the process where protein molecules clump together
Huh.
due to many forces, hydrophobic interactions, ionic interactions. Yeah.
Okay. When the interactions between the protein molecules is higher and better than the interactions between the protein molecules and the solvent, that is when aggregation happens.
Yes, sir.
Huh. And what about precipitation?
So that also results in decreased solubility.
Right. So, aggregates, although can be okay, aggregates need not be necessarily an issue with solubility, but rather a relative phenomenon where protein molecules tend to associate with themselves as higher order oligomers compared to be dispersed in solution. Whereas precipitation is a phenomenon that is specifically related to solubility. The protein preferentially is very less soluble in your solution, so it clumps together. And this forms a precipitate, that is precipitation. So these two factors can in a way be called as factors that happen when there is reduced solubility. So these two can be eliminated. Then we have salting in and salting out. So what one needs to understand with respect to salting in and salting out is at different concentrations of salt, the interactions between the salt and your buffer and your protein would determine its solubility. At a specific concentration, your protein solubility will be improved by addition of salt. So in labs, when we do protein purification, we add from 150 millimolar NaCl or KCl to 300 millimolar NaCl or KCl, one of these salts. This would improve the solubility. We would not add lesser or more. until we optimize the purification conditions. This phenomenon where we add salt to improve the solubility is called as salting in. There is an opposite phenomenon where more salt than what is required, that is beyond 300 millimolar, when added to your solution, that would form clouds of interactions such that your proteins are again forming aggregates. This is called salting out. Was that clear? The image for this will be given in the presentation. Now, this because of this internet connection, I'm not able to show the image. You can refer to the last slide of the PPT for this. But is the topic of salting in and salting out clear to you all? Oh, okay. Uh, yeah, with this, we come to the end of today's class. Uh, if there are any questions, you can ask me, or we can end the class. Okay, we'll end the class here today if there are no questions. Thank you.